So now that we know what a matrix exponential is, let's state why we care about them. Well, remember, we started this lecture off by looking at a system of ordinary differential equations. And that system manifested itself as what's called an initial value problem, which was u prime of t equals a times the vector u, where u of 0 is equal to a constant vector u naught. The reason matrix exponentials are so useful is that matrix exponentials can be used to solve this initial value problem. So what the official theorem says is that this initial value problem is uniquely solved by a single solution, vector u of t, and this equals the exponential of a times t multiplied by the constant vector u sub 0. Now, how would we use this theorem in practice? In practice, what we would do is we would try to diagonalize our matrix A as x times d times x inverse. And then if we apply this formula, which I call the similarity rule for matrix exponentials, this would tell us that our solution to the system further simplifies as x times the exponential of d times t times x inverse times the constant vector u0. So we can actually calculate this thing as long as we can diagonalize A, because calculating the exponential of a diagonal matrix is easy. So the point here is that matrix exponentials can be used to solve systems of ordinary differential equations. So let's go back to our example here. Here we were looking at a diagonalization of the form A equals x times d times x inverse. Let's say now that this matrix A was the coefficient matrix in our initial value problem, and that the initial values in the vector u were -3 and 1. What our theorem from the previous slide says is that this initial value problem is uniquely solved by a function or a vector function u of t, which equals, what's our formula here? This should be x times the exponential of d times t times x inverse times u sub 0. So the hardest thing to calculate here is the exponential of dt, but the exponential of dt is easy because d is diagonal. So this is e to the -7t in the upper left-hand corner, because in d, the upper left-hand corner is -7. And in the bottom right-hand corner, we get e to the 2t, because in the bottom right-hand corner of d is the number 2. So now all we need to do to get our solution to the initial value problem is multiply these expressions together. X times the exponential of dt times x inverse times u0. I did this multiplication earlier, and I got the first coordinate of u of t is -3 times e to the 2t, and the second coordinate is e to the 2t. So if we can diagonalize our coefficient matrix A in our ordinary system of differential equations, we can write down the solution to that ordinary differential equation, which involves the exponential of the diagonal matrix in our diagonalization. So this is one of the great applications of diagonalizations.